All right, welcome everyone to the next lesson in this series. And in this video, we will look at network encryption for Kubernetes using Calico and Wireguard. Now, in this series, we've spoken a lot about pod-to-pod communication. And we've also looked at the underlying plumbing associated when one pod in one node communicates to another pod in a remote node. Now, in such a communication flow, traffic has to egress the source node and traverse the network and then ingress the destination node and then reach the destination pod. Now, in Kubernetes, by default, when traffic traverses the network, it is not encrypted. Kubernetes natively does not provide network encryption. And what this means is if someone were to sniff the packets in the network, they will be able to reconstruct the payload that is being transmitted. Now, most applications have some kind of transport layer security via MTLS, but I've seen plenty of applications in the wild without transport layer or application layer security. But even if all the applications in the cluster have some kind of application layer encryption, you could still ascertain quite a bit of information about the cluster by sniffing control plane traffic, such as, for example, DNS. So as you build out your cluster, especially if you're hosting them in the public cloud or in a managed data center, it is very important that you consider network layer encryption for the cluster. All right, so in this lab, we will look at how you can turn on WireGuard using Calico. It's pretty much a toggle of a switch, but we're going to explore some of the theoretical concepts as well as what happens under the hood when WireGuard is configured in a Kubernetes cluster. So some of the concepts out of the way, when you enable WireGuard in a cluster, what happens first is a static key gets generated in each of the nodes in the cluster. Now this key has a public key as well as a private key. Calico retrieves the public key from each of the nodes and distributes it amongst all the other nodes in the cluster. So that way each node is aware of its remote peers as well as the public keys associated with those peers. Now, WireGuard also generates a separate key for sessions, and that key is derived using static keys as well as ephemeral keys. So these two go as inputs to derive what is known as the session keys. And these session keys are periodically refreshed every 2 minutes or so in a cluster, and we will look at that in the lab as well. Now, the reason session keys are derived using ephemeral keys is for a very important concept known as perfect forward secrecy. So consider a scenario where someone captures encrypted traffic from the network, and somewhere down the road in the future, they obtain your keys. They will be able to decrypt the packets. However, since WireGuard generates session keys that are periodically refreshed, using ephemeral keys that are only stored in memory, a malicious actor will not be able to retrieve your keys on a future date. And that is how you ensure perfect forward secrecy. Now, in this document, I have listed some other concepts as well and gone into the details of how the cryptographic primitives are derived. I'm not going to cover all of that in the video, but we will cover some important concepts. Now, for key exchange to generate the shared secrets, including the static keys as well as the ephemeral keys, WireGuard uses curve 25519 as the algorithm and CHA-20 to encrypt the payload using the session keys. Now, there's an authentication component as well, and what authentication ensures is that the receiver is able to validate the identity of the sender as well as make sure that the packets have not been tampered with. And WireGuard uses Blake 2S for deriving the session keys as well as generating the hash out of the payload that also feeds into authentication. All right. Now, if you're interested in reading more about the cryptographic primitives and the role that they play in encryption, its inputs as well as the outputs for each of these primitives, I have documented that in this lab guide. Okay. So next, let's go into the lab and look at how we implement WireGuard in a Kubernetes cluster. Let's get started. Alrighty, I have already gone ahead and deployed my lab. You will find this lab in folder number 13-WireGuard. And once you have provisioned the lab, make sure that you export the kubeconfig file, and then you could do a kubectl get nodes to make sure the lab is accessible. All right. So this is a simple 3-node Kubernetes cluster, we have a control plane and two workers, very similar to some of the other labs. And next, I'm going to do a kubectl get pods. We have two pods that we're using to demonstrate encryption, a backend API, and a front-end client querying that API. Now, these two pods are sending sensitive information through the wire, and let's look at how we can secure them using Wireguard. So first off, when you do a kubectl get Felix and grep for Wireguard, you're either not going to get an output or your output will be false, which means in this cluster, we have not enabled Wireguard. Okay. And you can also further verify this by checking for Wireguard information in the node. So in this node, which is Wireguard worker node, which is my worker one. In this case, I'm doing an IP link show type Wireguard and confirming that there are no Wireguard interfaces in the node. So basically in this cluster, encryption is disabled. So what we're going to do next is we're going to run a command, and basically this command is going to capture some packets from worker 2. And as you can see, I'm able to sniff sensitive information out of network packets between worker 1 and worker 2, basically between the front-end client and the backend API, right? So let me quickly open up a diagram here. So in my cluster, I have the front-end client and the backend API. And in this cluster, we haven't enabled encryption. So as traffic traverses this network, I'm basically sniffing this interface in worker 2, and I am able to retrieve some sensitive credentials from the traffic between worker 1 and worker 2. Just bear in mind that in the diagram, the interface here is ETH1, but in the lab, it's ETH0. That I'll probably correct that in the final diagram for the lab. All right, so with that, let me clear my screen. And next, let's look at the full HTTP payload as well between the two nodes. And if I run a TCP dump, as you can see, I am able to retrieve HTTP payloads from the network interfaces and potentially reconstruct the messages between these two workloads, all right? So this is the risk of not running encryption, especially if your nodes are hosted in a network that you do not completely control. So next up, we are going to enable Wireguard in this cluster. It's very simple. It's just a single command, a single Felix configuration to enable Wireguard. So I'm going to go ahead and do that. And as you can see, the Felix configuration has been patched. And next, if I do a kubectl get Felix configuration and grep for Wireguard, we now see that Wireguard has been enabled for this cluster. And we can also verify that by looking at an IP link show on a worker node. And as you can see, a Wireguard interface has now been created in the worker node. All right. Perfect. So with Wireguard enable, next let's do a Wireguard show on the same worker node. And this output basically provides the remote peers from the perspective of this node, as well as the public keys associated with those peers, the endpoint IP of those peers, as well as the remote IP addresses for the peers. And this is based on the IPAM assignment for those peers. And this is configured by Calico. So Calico goes into all of the nodes and configures the remote IPs as well as the allowed IPs for each of those remote peers. And if you look at the first peer, which is worker 2, in this case, we can see that there was a handshake that took place 51 seconds ago. So let me run that command one more time. And we see that there was another handshake that took place about 1 minute and 50 seconds ago. Let me refresh that again, 1 minute and 59 seconds ago. And you see another handshake that took place like 3 seconds ago. So every 2 minutes or so, there is a handshake that takes place that generates the session keys. And the session keys are derived, if you remember, using the ephemeral keys as well as the static keys generated for each of the nodes. So it's the session keys that ensure perfect forward secrecy. Now we have traffic between worker 1 and worker 2, and that's why you see transfers between worker 2 peer, which is worker 2 over here. However, we don't have any flows between worker 1 and the control plane node, and that's why you don't see an existing session. But if we were to initiate traffic a session will get created and you could see bytes being transferred as well. All right. Perfect. So let me clear that output. So next, let's capture some packets from the interface in Worker 2. Now, this time around, when you do the TCP dump, what you're going to see is packet destined to port 51820, which is the Wireguard port, and you see the UDP packets, which is what Wireguard uses for encapsulation. So now in this cluster, network flows between Worker 1 and Worker 2 are being encrypted. So this is what the WireGuard encrypted packet looks like. There is a payload that gets encrypted, and there is a UDP header, which is what we see in the packet capture. And you're also going to have the outer layer 3 headers with the source IP of the source node and the destination IP of the destination node and the associated Ethernet headers as well, so that the packet gets forwarded in the network. Now, one thing to note is, let me do another TCP dump on worker 2. If you look at the source and the destination IP, the source IP corresponds with the source IP of the node, and the destination IP corresponds with the destination IP of the node as these packets are being sent out of the network. Okay. All right. So perfect. So with that, let's go back to the lab and let's try to get a packet capture of those, HTTP payloads we did previously as well. And this time you're only going to see encrypted traffic. So we are not able to now retrieve those sensitive credentials from the network. All right, so next up, we're going to look at some of the underlying routing associated with how these packets get forwarded. Now, if you look at the routing table of a worker node, so in this case, I'm looking at the routing table of worker 1. If you look at the IP rules, there's going to be this special rule. So rule 99 over here. If you look at the rule, any packet that doesn't have this FW mark is going to get looked up by table 1. So if I do a output for table 1, this is what it looks like. So as the packets hit the routing table, if they are destined to any of these remote IPs, and these are based on the allowed IPs that we saw in the WireGuard configuration, that packet is going to get forwarded to the WireGuard interface, which will do the encryption as well as the encapsulation for that packet. All right. So basically going back to the diagram. So let's say a packet comes in from a source pod. There's going to be a lookup using the IP rule, a lookup to table 1. And if the packet matches a remote destination as configured by the allowed IPs in WireGuard, that packet is going to get forwarded to the WireGuard interface. This does the encryption, the encapsulation, the packet gets punted out the Ethernet interface and reaches the remote destination. And given that the packet has the well-known WireGuard destination UDP port, as it enters the remote node, it's going to get forwarded to the WireGuard interface, which does the decryption and then sends the packet off to the destination port. Okay, so this is how the routing works under the hood for WireGuard encryption. All right. Okay, so going back to the lab, you could disable WireGuard in the cluster as well. Like I said, it's simply a toggle of a button. So go ahead, try that, do that. You can re-enable WireGuard. And basically, that's pretty much it for the lab. It's relatively straightforward to configure, but it's also important to know some of the underlying concepts as well as what happens under the hood from a routing perspective. So I hope you enjoyed this lesson. That's it for this video. Thanks for watching. I'll see you in the next one. Bye for now.